In the third of 3 videos on optimization theory, we will complete our discussion of continuous problems, in particular covering linear and nonlinear inequality constraint problems, and also deal with integer and mixed integer problems. First, to discuss continuous linear inequality constraint problems. So we're going to consider problems of the form minimize over choices of x in Rn, the objective f of x, subject to ax equals b, they are the equality constraints, and also subject to cx less than or equal to d, the inequality constraints. A, b, c, and d are suitable constant matrices and vectors, and as I mentioned, cx less than or equal to d are called the linear inequality constraints. Let's turn to some optimality conditions. Suppose that f is partially differentiable with continuous partials, and we'll consider our minimization problem. If x star is a local minimizer of that problem, then there exist Lagrange multipliers lambda star in Rm and Lagrange multipliers mu star in R to the R, such that the following conditions hold. These conditions generalize the conditions in our previous types of continuous optimization problems. For an unconstrained problem, the gradient of f evaluated at x star would be equal to 0. For an equality constrained problem, the gradient of f at x star plus A transpose lambda star would be 0. Here, in inequality constrained problems, we have an additional term, C transpose mu star, just as the term A transpose lambda star was offsetting the desire to minimize f against the need to satisfy the constraints, the equality constraints. In this case, in addition, the term C transpose mu is also dealing with the need to satisfy the inequality constraints. Some of the terms that we've seen before are the equality constraints need to be satisfied. Certainly if x star is feasible, ax would equal b. Given our inequality constraints, for x to be feasible, cx star should be less than or equal to d. But 2 new lines, qualitatively new lines compared to our previous conditions, are the second line here and the last line. The second line is called the complementary slackness constraints, and it has the following interpretation. By the way, that capital letter there is capital mu, and I'll mention a notational device. Whenever I've got a vector, in this case mu, that is a vector denoted by a lowercase letter, I will use the corresponding uppercase letter to represent a matrix, a diagonal matrix, that is to say a matrix that zeros everywhere except its diagonals, and its diagonal entries are the entries of the vector mu. When I multiply that matrix into Cx minus d, it has the effect of multiplying for each L, mu L star into the lth row of C times x star minus dl. Requiring that to be equal to the 0 vector means that for each L, either mu L star will be 0 or the lth row of C times x star minus dl will be 0. In other words, either the lth entry of mu is 0 or the lth constraint is active or binding. The last constraint here is non-negativity on mu. So those constraints that mu star Cx minus d is equal to 0, as I mentioned, are called the complementary slackness conditions, and as I said, they require that for each L, either the lth inequality constraint is binding, in other words, satisfied with equality, or the lth Lagrange multiplier is equal to 0. Let's try this out on an example problem. It had quadratic objective, equality constraint specifying a particular line, and an inequality constraint. The objective and constraints are specified on this slide. Objective is quadratic, constraints and matrices as follows. We've already seen that the solution of the problem is x star is equal to 3, 3, and I claimed that that x star together with Lagrange multiplier lambda star equals minus 4 on the equality constraint, and mu star equals 4 on the inequality constraint satisfy my conditions. Let's try it out. First of all, the gradient of f is this diagonal matrix times x plus a constant. And so adding that together with A transpose lambda plus C transpose mu gives us these three terms. Plugging in my claimed lambda star and mu star adds everything up to 0. How about the complementary slackness constraints? Well, the one inequality constraint is binding, so Lagrange multiplier times constraint equal to 0 is satisfied because the constraint is equal to 0. And of course, the equality constraint is satisfied. The inequality constraint is satisfied, and the non-negativity on mu is satisfied. The idea behind the non-negativity on mu is as follows. When we had equality constraints and we had a objective, if the unconstrained minimizer of the objective would be on one side or the other of a particular set satisfying the equality constraint, then we needed to be able to offset that unconstrained minimizer in order to find a point that was on the feasible set. In other words, whether the unconstrained minimizer was, let's say, on the left-hand side of the set representing an equality constraint or on the right-hand side, we had to be able to pick a Lagrange multiplier that pulled the minimizer towards the feasible set. That corresponds to the Lagrange multiplier on equality constraints being able to be either positive or negative. On the other hand, when we have an inequality constraint, if the unconstrained minimizer would be on the feasible side of that inequality constraint, then we don't want to affect it at all. If it would be on the infeasible side, we need the Lagrange multiplier to pull it back onto the feasible region. Since we only need to have the Lagrange multiplier pulling in one direction, that implies that we only need Lagrange multipliers of one sign on inequality constraints. So, to summarize, the Lagrange multipliers again adjust the unconstrained optimality conditions to balance the constraints against the objective. And since the inequality constraints only need to be enforced in one direction, the Lagrange multipliers on the inequality constraints are restricted in sign. Those equality and inequality constraints in 437, we'll again refer to them as the first order necessary conditions, although strictly speaking they include the other conditions in the hypothesis of the theorem. These conditions are sometimes called Kuhn-Tucker point or Kuhn-Tucker conditions or Karush-Kuhn-Tucker conditions, and a point satisfying them is called a KKT point. Remember, we had the notion of a Lagrangian. In the case of inequality constraints and equality constraints, our Lagrangian was a function of x, lambda, mu, and it equaled f of x plus lambda transpose times ax minus b plus mu transpose times cx minus d. As in the equality constraint, we can define the gradients of L with respect to x, with respect to lambda, and with respect to mu. And if we write them down, they reproduce some of the terms in the first order necessary conditions. We need to set the first term equal to 0 in the first order necessary conditions. We need to set the second term equal to 0, but we need to interpret the third term as inequality constraints. Furthermore, we need to add the complementary slackness conditions and non-negativity on mu greater than 0, as well as interpreting Cx as being less than or equal to D to reproduce the first order necessary conditions. Theorem 4.12 says that if the hypotheses are satisfied and if f is convex, then x star is indeed a global minimizer of the Lagrangian for lambda star and mu star equal to the Lagrange multipliers. Again, we'll utilize that in our profit maximization interpretation when we want to define prices. Indeed, paralleling our earlier discussion, if we interpret the Lagrangian as minus the profit plus a constant term, finding the minimizer of the Lagrangian is equivalent to finding the maximizer of the profit. And again, the prices lambda star and mu star provide a compensation for operating costs incurred by the firm so that unconstrained maximization of profits is consistent with minimizing the operating costs subject to the equality and inequality constraints. Let's specialize for a moment to convex problems. That is to say, f is partially differentiable with continuous partials, a, b, c, d appropriate matrices, and we want to find the minimizer of f subject to ax equals b, cx less than or equal to d. If x star, lambda star, and mu star have the following properties, well, that f is convex on the feasible set, and if x star, lambda star, and mu star satisfy the first order necessary conditions, then x star is a global minimizer of our problem. In addition to the first order necessary conditions, this requires that f is convex on the feasible set. And if that's the case, the first order necessary conditions become sufficient for finding a global optimizer. Again, we can look at an example. We'll consider problem 4.10. We've already seen the Lagrange multipliers, and we see that they satisfy the first order necessary conditions. Since f is twice continuously differentiable with continuous partial derivatives, its Hessian is constant and positive definite. Therefore, a point x that satisfies the first order necessary conditions, x star, lambda star, and mu star, that satisfies the first order necessary conditions will also be sufficient for global optimality. We can also introduce a notion of duality here for an inequality constraint problem. We can define a dual problem where the role of variables and constraints is either partly or fully swapped. We're again going to recall some of the discussion in section 4.2. Remember the dual function. The dual function is the inf of the Lagrangian. The effective domain of the dual function is the set of points where the dual function is greater than minus infinity. And E is convex, D is concave on E. Let's see an example of this. We'll consider our inequality constraint problem with the quadratic objective linear constraints. The Lagrangian is the objective plus a term determined by the equality constraints multiplied by lambda transpose plus a term determined by the inequality constraints multiplied by mu transpose. Since we've only got one equality constraint and one inequality constraint, we've simply got the objective plus term in the lambda plus a term in mu. For any given lambda and mu, that Lagrangian is strictly convex. We can minimize it by setting the gradient of Lagrangian with respect to x equal to 0. And by corollary 4.8, those first order necessary conditions are also sufficient. Indeed, we can solve for that and we'll find a unique minimizer. And that will enable us to evaluate the dual because that enables us to find the minimum of the corresponding inf. In particular, here is the gradient of the Lagrangian, and if I set that equal to 0, I can solve it by rearranging for x in terms of lambda and mu. Let me think of x as depending on lambda and mu, and I'll denote that by superscript. I can write x of lambda and mu is equal to minus the inverse of this diagonal matrix times these terms. Multiplying that out, I get a constant term plus a term in lambda plus a term in mu. If I substitute that back into the Lagrangian, I can evaluate the dual function for any particular value of lambda, and that gives me minus a half lambda squared minus a quarter mu squared minus 2 lambda minus a half mu lambda. The dual problem is to maximize over the lambda and mu in the effective domain the dual function subject to mu greater than or equal to 0. Continuing with the problem we just looked at, here's the dual function, and it's twice partially differentiable. Here's the gradient of the dual. The first term is the derivative with respect to lambda. The second term is the derivative with respect to mu. The Hessian is given by this matrix, and I claim that lambda star mu star equal to minus 4, 4 maximizes the dual. Why is that? Well, in particular, if I plug that lambda star mu star into the gradient, it equals 0, so that means I satisfy the first order necessary conditions. Furthermore, mu star happens to be strictly positive, and the Hessian of D is negative definite. Consequently, if I were not paying attention to the constraint on mu, we would have observed that lambda star mu star given by minus 4, 4 would be the unconstrained maximizer of the dual over all lambda and mu. If I restrict myself to any lambda but mu greater than or equal to 0, I couldn't possibly do any better, because in particular my value of mu is already, it couldn't possibly do any better, but moreover my value of mu star happens to be greater than or equal to 0. So this means that the value I exhibited, lambda star equal to minus 4, mu star equal to 4, is the unique maximizer of the dual problem, maximize the dual over lambda over mu greater than or equal to 0. We can also consider sensitivity analysis. This time we would perturb the equality constraints by gamma and the inequality constraints by eta. Again, I need some technical conditions. I need f to be twice partially differentiable. X star should be a local minimizer for the base case values where gamma is equal to 0 and eta is equal to 0. And let me assume that there are Lagrange multipliers lambda star and mu star. Moreover, I need a particular matrix to have linearly independent rows. That matrix A hat consists of the m rows of A together with the rows CL of C corresponding to binding constraints. If that matrix has linearly independent rows, and furthermore, if I look at the Lagrange multipliers on the inequality constraints, if any of them are binding, I need to have that their Lagrange multipliers are non-zero. In other words, there are no inequality constraints that are binding with corresponding values of Lagrange multipliers 0. And furthermore, again considering this matrix A hat, for any delta x such that A hat delta x is equal to 0 and x delta x is not equal to 0, I need this expression to be greater than 0. Remember, we referred to this previously as the Hessian is positive definite on the null space of A hat. Well, if those conditions hold, then for gamma and eta in a neighborhood of the base case values, there's a local minimum, local minimizer, and Lagrange multipliers. And moreover, if we consider the local minimum and consider its sensitivity to gamma and eta, then the sensitivity to gamma is lambda star transpose, the sensitivity to eta is mu star transpose. Again, the Lagrange multipliers yield the sensitivity of the objective to the right-hand side of the equality constraints and the right-hand side of the inequality constraints. The sufficient conditions for the sensitivity theorem are fairly stringent and are not always satisfied by the problems we studied. For example, Theorem 14 doesn't apply directly to linear programming problems. However, sensitivity analysis can be applied to linear programming, and we get fairly similar results. As with linear programming in general, the linearity of the objective and the constraints leads to various special cases. And indeed, the Lagrange multipliers associated with the constraints give us sensitivity results and very powerful economic insights. Let's see an example of the sensitivity analysis. Same problem as before, and at the base case we have this matrix A hat. It's a matrix with linearly independent rows. Furthermore, del squared f is positive definite, so in particular it's positive definite on the subspace. And let's suppose we changed our inequality constraint from Cx less than or equal to D to Cx less than or equal to D minus eta. If eta is small enough, then the minimum of the perturbed problem differs from the minimum of the original problem by approximately mu star transpose eta. In other words, mu star times eta, since we have a scalar. The final type of continuous problems we're going to look at are nonlinear constrained, where our equality constraints are defined in terms of a general, potentially nonlinear function. G goes from Rn into Rm, and the inequality constraints are defined in terms of a general inequality constraint function H that goes from Rn into R to the R. Again, we need some technical conditions to get simple versions of our theorems. The technical condition in this case is on X star. That will be a potential minimizer, a candidate minimizer of my problem. X star is said to be a regular point of the constraints gx equal to 0 and hx less than or equal to 0 if X star satisfies the constraints, if g and h are both partially differentiable with continuous partial derivatives, and if the following matrix has linearly independent rows. It'll have a very similar role to the role of the analogous matrix in the linear constraint case. A hat consists of the m rows of the Jacobian of G, and together with the rows, let me call them KL, of the Jacobian K of H, again evaluated at X star. Which rows am I going to pick? I'm going to pick the rows that correspond to active constraints. Recall in the linear case, we had the equality constraint matrix A. In the nonlinear case, the counterpart of that is the Jacobian. In the linear inequality constraint, we had the rows CL of the inequality constraint matrix. In the nonlinear case, that corresponds to the rows KL of the Jacobian K of the function H. And again, we only use the ones corresponding to the binding constraints. So my optimality conditions will need me to assume that X star is a regular point. Let's suppose we have function f, g, and h. Let j and k be the respective Jacobians. We want to minimize over x's in Rn, the objective f of x, subject to gx equal to 0 and hx less than or equal to 0. Let's suppose that X star is a regular point of the constraints gx equal to 0 and hx less than or equal to 0. We just defined a regular point. Then, if X star is a local minimizer, we have the following optimality conditions. These should look very similar to the conditions for equality constraints. We have a term that has the gradient of the objective. In the linear case, it had an A, but now that's replaced by the Jacobian transpose times lambda star. Another term in the linear case would have had C in it, now replaced by the Jacobian of H. We have complementary slackness constraints. They say that for each constraint, either the Lth Lagrange multiplier is 0 or the Lth constraint is equal to 0, is binding. We need the equality constraints to be satisfied. We need the inequality constraints to be satisfied, and again we have non-negativity on the Lagrange multipliers. So as previously, these are the first order necessary conditions, and the conditions are also called the Karush-Kuhn-Tucker conditions. We can again write these conditions down in terms of the Lagrangian. Remember the Lagrangian objective plus a term with the equality constraints, term with the inequality constraints. We can again reproduce some of the first order necessary conditions by taking the gradient of the Lagrangian. Let's see an example. We had a quadratic objective, equality constraints in terms of signs, inequality constraints in terms of signs. I claim that the following point, x star is 0.5, 1.5 pi on 6, lambda star is 6,1, and mu star is 5, satisfies the first order necessary conditions. Let's check it out. The gradient of f is 2x1, 4x2, 0. We can evaluate the Jacobian, evaluated at x star. We can evaluate the Jacobian of the inequality constraints, evaluated at x star. If we combine all of the rows of jx star together with the row of kx star, the inequality constraint is binding, we find that that 3 by 3 matrix has independent rows, so x star is indeed a regular point. And plugging in to the rows, to the entries in the first order necessary conditions, first constraint is satisfied, complementary slackness is satisfied, equality constraints are satisfied, inequality constraints are satisfied, non-negativity on mu is satisfied. So the point x star, lambda star, and mu star satisfies the first order necessary conditions. We can also develop sensitivity analysis, and again the Lagrange multipliers provide information about sensitivity to changes in the constraints. Now I want to turn to integer problems. In some of our problems, in some formulations, we're going to see that the entries of the decision vector must be integer valued. A good example of this is that the decision to have a generator on or off in unit commitment is binary valued. Combined cycle gas turbines, combined cycle generating units, typically have multiple operating modes. Off, one gas turbine operating, one gas turbine and one steam turbine operating, two gas turbines operating, two gas turbines, one steam turbine, for example. So we need to represent, in that case, the commitment decision as an integer. So I'm going to write the set capital Z for the set of integers. And an integer programming problem seeks the minimum and minimizer over choices of a decision variable that lies in some subset of the n-fold Cartesian product of Z with itself. In other words, an n vector of integers. To emphasize that our variables are no longer continuous, I'm going to typically use the symbol Z for decision vectors with entries that are integer valued. Let's see an example. Suppose that S in Z squared is the set of points Z such that Z1 is either 0 or 1. The first entry of Z is either 0 or 1, or the second entry is 0 or 1. So if I plot that, here's Z1. This could be the commitment decisions for generator 1, generator decisions for generator 2. Either both entries are 0, one of them could be 1 and the other one 0, or vice versa, or both of them could be 1. And you can see that this set is non-convex. Integer programming problems generally have non-convex feasible sets. And the feasible set in the example is non-convex since a line drawn between any 2 points in the feasible set does not lie entirely in the set. Because of that non-convexity, iterative improvement algorithms usually cannot solve for global optimizers of integer programming problems. And the implication is that general purpose algorithms tend to be extremely computationally intensive. Some particular problems can be solved efficiently, but generally speaking, it's a significant computational effort to solve an integer programming problem. Let's think a little bit about types of problems. Similarly to continuous variable problems, we can consider integer problems with feasible sets that are defined in terms of equality constraints and inequality constraints. And commercial software for integer programming is available for integer linear programs. In other words, I want to minimize over choices of Z in Z to the n, linear objective, C transpose Z, subject to linear equality constraint, AZ equals B, and subject to CZ less than or equal to D. There's also a limited amount of integer quadratic programming software available. But because of the non-convex feasible set, it's generally the case that there is a duality gap between the primal and dual formulations of integer programming problems. And consequently, that means that in our profit maximization interpretation, there will generally not be a way to find a price that induces a profit maximizer to behave consistently with minimizing costs subject to the constraints. We won't be able to simply use the maximizer of the dual as prices. So this means, for example, in an electricity market that includes unit commitment, a day ahead electricity market is an example, we are going to need more than prices on the energy supply demand balance to induce generators to be committed consistent with minimizing the costs. And in order to do that, we'll see that typically in electricity markets we make side payments that are designed to induce behavior that's consistent with minimizing overall costs. Well, sometimes our problems not only have integer variables, but also have continuous variables. Such a problem is called a mixed integer problem. So, as well as the decision to have a generator on or off, a unit commitment problem being binary variable, we also typically need to specify the production level of an in-service generator, and that will typically be continuous value. So a mixed integer programming problem is attempting to find the minimum minimizer over choices of decision variables such that some entries have integer variables, some have continuous variables. Here's an example of a feasible set involving both integer and continuous variables. Set P is the set of points z, x, such that z is in 0, 1, and such that 2 times z is less than or equal to x is less than or equal to 4 times z. When z is 0, this requires x to be 0. That's the dot, the bullet down at 0, 0. When z is 1, it requires x to lie between 2 and 4. Notice that my feasible set is the union of one point and a line interval, and that makes the set non-convex. This would be a typical example of a feasible set for a generator. If it's off, it's generating nothing. If it's on, it can generate between its minimum and maximum production level. But again, because of the non-convexity of the feasible set, general purpose algorithms are quite computationally intensive. There is commercial software for mixed integer programming, mixed integer linear programs, mixed integer quadratic programs, but as with the integer programming problems, there is usually a duality gap, and this will have implications for prices. Let's see how the duality gap might arise. I'm going to consider a problem where I want to minimize an objective f that's a function of z and x, subject to a quality constraint g such that zx is equal to 0, and I'm minimizing this x and z over the set P. The set P is that feasible set we defined a moment ago. The function f is the cost function of my generator. When it's off, z is 0, x has to be 0, and the cost is 0. When it's on, z is 1, x can be between 2 and 4, and its cost is going to be 4 plus x. 4 we can think of as the intercept of the cost function extrapolated back to x equals 0. It's the no-load cost for my generator. It's the cost of running the auxiliary equipment. When I'm generating above 0, I incur additional costs, and that will vary with my production. My equality constraint is going to be 3 minus x is 0. We met that one before for a similar type of example with a generator. So if g of zx is 0, then the demand 3 equals supply x, or to put it another way, supply equals demand. So the generator has two variables associated with its operation, a commitment variable z, production variable x. To meet a demand of 3, the generator has to be on. So we know that z star has to be 1. Z star is the optimizer of the problem. I'll use z star for the optimizer of the problem. Furthermore, the production has to match demand. So x star has to equal 0, has to equal 3. So the only feasible point, and that has to be the minimizer of the problem, is z star equal 1, x star equal 3. For that value, the minimum is 4 plus x star, or 7. Let's consider the dual function with respect to the equality constraint. If I dualize the problem, I create a dual function. The dual function is the inf over choices of x. Because I did not dualize the constraints on my generator feasible set, I'm going to keep them explicitly, and I'm just going to dualize the equality constraint on supply-demand balance. So that means that my dual function is just a function of lambda, the dual variable on my equality constraint, 3 minus x is 0, and my Lagrangian is the objective plus Lagrange multiplier times 3 minus x. Remember, that means I'm going to keep explicitly the minimization over my feasible set of my generator. I want to, for any given value of lambda, minimize zx over p. Takes a few details to do it. We need to consider various values of lambda and also to understand the structure of the objective. But it turns out that the best way to analyze it is to consider various cases. For lambda less than or equal to 1, it turns out the dual function is equal to 3 lambda. For lambda between 1 and 2, the dual function is 3 lambda. For lambda equal to 2, the dual function is 3 lambda. And for lambda greater than 2, the dual function is 8 minus lambda. So we can think of maximizing the dual function over values of lambda, and it turns out that the dual maximizer is lambda star equal to 2. And at that point, the dual evaluated at lambda star is 6. Ooh, remember that the original minimum was 7, whereas the maximum of the dual is 6. That means we have a duality gap. And furthermore, the corresponding value of x corresponding to lambda star equal to 2 does not meet demand. Let's investigate that. If we plug in lambda star equal to 2, we find that the Lagrangian has two minimizers, either x equals 0 or x equals 4. And that's indeed illustrated here by the dotted line. For lambda that's smaller than 2, the generator's off and isn't generating anything. For lambda greater than 2, the generator would, from a profit maximization perspective, would like to be on and generating at 4. So the corresponding value of x does not meet demand. There's a duality gap. As I said, the objective of the primal problem is 7, which is greater than the objective of the dual maximizer. So no price in this case for production will equate supply to the demand of 3. For lambda less than 2, a profit maximizing firm is going to produce nothing. For lambda equal 2, a profit maximizing firm is indifferent between producing nothing and producing 4 units. And it prefers either of those to producing at any other level. For lambda greater than 2, a profit maximizing firm will want to produce 4 units. Whenever there is a duality gap, such as this example, there will be no prices on the dualized constraints that will induce profit maximizing firms to satisfy the constraints. We'll see that we need side payments separate from the prices on the dualized constraints that need to be used in order to induce the right behavior. We'll come to that when we discuss unit commitment. So, to summarize, in this chapter we have defined several optimization problems. We illustrated particular types of problems with some elementary examples. We defined the notion of convexity, and we looked at local and global and strict and non-strict minima and minimizers. We looked both at continuous but also integer and mixed integer problems. Duality and optimality conditions for continuous problems were presented, and we defined integer and mixed integer problems. The implications of dualizing non-convex problems were explored. We'd earlier explored the implications of dualizing convex problems. There are also a number of exercises at the end of the slides in this section, in this chapter, that you can look at to make sure that you understand the material.